So when we have a geometric series, the geometric series can be decreasing. And if it's decreasing, what happens as it keeps decreasing? Now, we saw a problem like this before where we looked at a value of something dropping and decreasing and decreasing and decreasing. Eventually, that decreases to zero. So what's going to happen here is this sequence eventually goes to essentially zero. Never really quite zero, but essentially zero. And so what's happening to this sum of this as we just keep going and adding on, adding on, adding on? We're just basically adding on just tiny, tiny little bits. So what happens if we just keep going with this? Okay, well, let's just first of all find the Sn formula. So for this one here, there's my T1, okay, and I know that my multiplier is going to be times by 1/2. Okay, so there's my R. Okay, so when I write this out, my Sn formula is going to be A, so 20, times 1/2 to the power n. But right, use square brackets here. Okay, 1/2 to the power n minus 1. And that's all over 1/2 minus 1, which is going to be negative. Okay, so that's my Sn formula. Let's just simplify this a little bit. So this is going to be negative 20 divided by negative 1/2, which is negative 40. But this is also going to be negative. So instead of having my double negatives, I'm just going to make that a positive. So my Sn formula is going to look like this. It's going to be 40 times 1 minus 1/2 to the power n. Okay, so there it is. So using this formula, I'm going to calculate, okay, just going to plug it into my calculator. I'm going to calculate S10. So what's my S10 going to look like? Okay, so 40 bracket 1 minus bracket 1/2 to the power 10. And I'm getting a value of 39 point. So S10 equals 39.96 and a bunch of decimals. So I'm just going to round it to 96. Okay, S20, so I'll do the same thing, except I'm going to use 20. Okay, so you guys can go ahead and do that as well. Okay, so when I do that, whoa, what are you guys getting here? Because I'm getting 39.99996. Wow, come on, really, I'm just going to say it's about 40. Okay, because I don't really want to write so many nines in there. So I'm going to say about 40. And that didn't grow very much. So from here to here, we grew very little. And that's 10 terms. So how big are we going to get? I don't know. Let's keep going. I'm going to try 100 terms. And use a formula where n equals 100. And ooh, my calculator gives me exactly 40. Now I know it's not exactly 40. I think it's just I just overwhelmed my calculator. And even after 100 terms, my calculator just ends up kind of limiting out. And so this is what's happening. There, in fact, is a limit to how big this is going to get. Because what's happening is I'm going to basically be adding smaller and smaller amounts. At near the end, near infinity, I'm pretty much adding 0. So what happens is that as n gets large, Tn becomes insignificantly small. We're basically adding 0. So if r is less than 1, so if my multiplier is less than 1, that means that each term gets successively smaller and smaller and smaller and smaller and smaller. You're going to eventually hit 0. And that's what's happening here. So as n goes to infinity, Sn has a limit because this ratio to the power n, so r to the power n, goes to 0. Well, yeah, if r is less than 1, this is always going to get smaller, and as we multiply it more and more and more and more, we're eventually getting it 0. So this part of my formula becomes 0. And what ends up happening is I get this and I rearrange it into this. And so if if my series is infinite and it's getting successively smaller, as long as it's a geometric series, okay, it's different for other series, but for a geometric series, we know that it converges to a limit, and the limit is this formula here. So let's see if that actually applies in this case. Okay, so if I want to find the S infinity, so S infinity is going to be the limit of this formula, 1 minus r. Okay, so I start with 20. My r is 1/2. 1 minus 1/2 is 1/2. 20 divided by 1/2 is 40. Oh yeah, that's what my calculator gave me as well. So if I could do this infinitely, although technically I can't do it infinitely, I'm going to get a sum of 40. And this is what happens when we have an infinite geometric series. And when the r is less than 1, the infinite geometric series adding smaller and smaller amounts. That's important. That's a key point. If we kept on adding numbers that are bigger and bigger, it's just going to get bigger. But we're adding numbers that are smaller and smaller and smaller and tending towards 0. Right? So if I look at this sum sequence again, yeah, this number is tending towards 0. And I'm essentially going to be adding zeros near the end of this series, and it ends up having a limit. And the limit has this formula. Okay, so this is my formula for an infinite geometric series, and it only works if it's a decreasing function. Okay, it's geometric decay. So if I take a look at these seem to be decaying. Okay, so yeah, and this is, just double check, this is a geometric series. Okay, so 6 divided by 3 divided by 3 divided by 3, yeah. And I'm dividing by 3, and this must have a limit because it's getting smaller and smaller and smaller and smaller. So I know that I can use my S formula now, a over 1 minus r. I just need to establish the a value. My r value is times by 1/3, so 1 minus 1/3. So that becomes 6 over 2/3, and that becomes 9. Okay, I end up with a net sum of 9. So if I just add these together, in fact, even if I just add the first 4 terms, okay, and we're going to do this infinitely, but even if I just add the first 4 terms, 6 plus 2 plus 2/3 plus 2/9, I'm already getting pretty close to 9. It's 8.88888888. And the next one's going to be plus 2 divided by 27. That's going to give me 8.96, and it's going to get ever so much closer to 9 as I add successive terms. Okay, what about this one? Well, yeah, it's decreasing, and it's decreasing geometrically. I multiply, my multiplier here is negative 0.8 times negative 0.8, okay, etc. So I have a decreasing series. It's geometric, and it's going towards 0. So this must be an infinite sum, which I can use this formula for. So a over 1 minus, so a over 1 minus r. But in this case, r is negative. Now, how does that affect my sum? Well, it's going to make this sum not quite as big because parts of it is plus, parts of it is minus. And notice that the negative is going to make my denominator bigger, which makes sense, and because my total sum should be smaller than if it was positive, if these were all positive. Okay, so I'm just going to plug it in again. 1 minus negative 0.8. Okay, so it's going to be 27.7 repeating as fraction. That is 250 over 9. Okay, so that is my infinite sum. It's just going to keep on getting bigger, so it's going to go, I'm going to add and subtract, but as I'm doing it more and more, I'm going to add and subtract less and less, and then we end up with a finite sum. And the decimal value just works out to be 27.7 repeating. Okay. This next one here, if this goes on infinitely, well, each term is getting bigger and bigger. Well, if each term is getting bigger and I do this infinitely, well, this cannot have a finite sum. So we can't use this formula. Okay, it doesn't apply here, and our sum must be infinite. Okay, there's no other way to be able to evaluate that other than knowing that it's infinite.